Solutions concentrations can be measured in a tremendous number of different ways, including parts per million, parts per billion, molality, but the most common way that solutions concentrations are measured is using molarity. And molarity is notated with a capital M, and molarity is equal to the number of moles of solute divided by the liters of total solution. So it's frequently thought of that molarity is simply moles per liter. And that's really interchangeable. This capital M for molarity and moles per liter are interchangeable units. So let's consider the fact that if molarity is moles per liter, you can rewrite this equation to find that the number of moles of solute is equal to the molarity, or the concentration of the solution, times that solution's volume. Well, think about lemonade. If I had this glass of lemonade right here, and I thought to myself, man, this lemonade's just too sweet, you could pour some water into that lemonade and stir it, and that would have diluted the lemonade. Now, what did not change here, well, let's think about what did change actually. What does it mean to dilute something? Well, all that means to dilute something is to decrease the substance's concentration or its molarity by means of increasing its volume. So by pouring more water into this lemonade, I made the solution's total volume higher, but I made its molarity, its concentration, lower. But it's important to recognize that what did not change was the total number of moles of substance in that solution. In this case, that would be moles of lemonade. But since that number of moles of whatever in that solution didn't change, it's possible then to write that your initial molarity times your initial volume has to equal your new molarity times your new volume. By setting it up this way, you're able to do many calculations in order to help you determine how much water do I need to add to a given solution to make it reach a certain volume and concentration. For example, calculate the volume of 3.25 molar nitric acid that must be diluted with water to produce 500 milliliters of 1.25 molar nitric acid. I'm wanting to go from 3.25 molar down to 1.25 molar. Well, by adding water to this more concentrated solution, I will make it less concentrated. But I want to end up with 500 milliliters of this 1.25 molar solution. Maybe I need 500 milliliters for an experiment, and I don't want to make too much. Well, we can use our M1V1 equals M2V2 to solve for this. So, in this example, our initial concentration is 3.25. So that's our initial molarity of 3.25. We're looking for the volume of this 3.25 acid, that 3.25 molar acid that we have to add. So we'll just leave that as V1 equals the second molarity, or the new molarity, which I'm targeting 1.25 to be my new molarity, times my desired volume, or my ending volume, of 500 milliliters. Now the units don't matter here, but you have to be consistent. So I'll just leave this as 500 milliliters. And let's just solve for my initial volume. To 3 sig figs, I find that my V1 equals 192. Since this 500 right here was in milliliters, our volume down here will also be in milliliters. What this means is I must add water to 192 milliliters of 3.25 nitric acid in order to achieve 500 milliliters of 1.25 molar nitric acid. Well, this might not make any sense because I'm only using 192 milliliters of nitric acid. Where did the rest of this volume come from? That difference is due to the water that you added. Since you need 500 milliliters of total solution and 192 milliliters is coming from the concentrated acid itself, you actually need to add 308 milliliters of water. What this means is by adding 308 milliliters of water to 192 milliliters of 3.25 molar nitric acid, you will produce 500 milliliters of less concentrated 1.25 molar nitric acid. Now, when you go to do these dilutions in the lab, precision is very important, so you need to use one of these three more precise pieces of laboratory equipment. This one on the left is a volumetric flask. And the volumetric flask just simply has this little line on the stem to help you more precisely measure exactly the volume that that flask is calibrated for. For example, this flask is calibrated for 10 milliliters, so exactly at that line is the 10 millimeter mark. It's also possible to use this middle one, which is a graduated glass pipette. Now, you don't actually use graduated glass pipettes too often because they're more difficult to use than volumetric flasks, but they serve the same purpose. And this last one on the right has this valve called a stopcock that you can turn and let out exactly a precisely measured amount of liquid that's above it, and that's called a burette. More often than not, you will use a burette or a volumetric flask in order to do your dilutions. Now, a word of warning about diluting acids is that it's important that you always add acid first, but rather not first, but always add acid to water. So always add acid. You must always add the acid you are diluting to water. This will prevent the acid from bubbling or splashing as it heats up. Because if, say, you had a sample of acid and you added water to that, oftentimes as you dilute acids, it releases a tremendous amount of heat. So if you begin adding water, what can happen is this acid can heat that water up so abruptly that it can cause that water to boil and thus splashing acid upwards. So it's important that you always add acid to water. So it looks something more like you have water here and you're pouring the acid into it. That will allow it to immediately dilute and be much safer. So to go through the whole process, let's consider this problem. So a student needs to dilute 12 molar hydrochloric acid in order to obtain 100 milliliters of 1.25 molar hydrochloric acid. So first, let's just set up our MV equals MV to get some numbers. Initially, the molarity was 12, where we need to know how much 12 molar acid to add. We're striving to have a concentration of 1.25, and we need 100 milliliters of it. So when we plug this in, we find that V is 10.42 milliliters. Now you have to understand what this means. This means you need 10.42 milliliters of the concentrated acid, but since the final solution has a volume of 100 milliliters, the remainder of that must be the water that's being added. So 100 minus 10.42 is 89.58 milliliters. This 89.58 milliliters is the water that will ultimately be added in combination with 10.42 molars of the acid to produce 100 milliliters of 1.25 molar acid. Okay, so I've got a burette set up. It's important that you read this the proper way. Notice we know for a fact that the reading of this burette is between 39 and 40. You'll also notice the burette is written upside down. That's not such a big deal right now, but we know for a fact this is between 39 and 40. And each one of these little ticks over on the left side is 1/10 of a milliliter. So we know for a fact, and we're going to read the meniscus, that it is beneath this tick and the actual 40 tick. The meniscus is falling between this last tick and the large tick for 40. So we know that it is 39.9. We know for a fact it's between 39.9 and 40. So since we have not yet estimated a digit, we get to estimate one more digit. And since this meniscus is only a little bit below that 39.9, I feel comfortable saying this reading is 39.91 milliliters. So since this is reading backwards and we need to apply 10.42 milliliters of acid, we will, instead of subtracting, we will actually add 10.42 milliliters to this. So that would show a reading of 50.33 milliliters. This means we need to open this burette and drain the strong acid into the water that we're going to be adding it to until the burette reads 50.33. Since the burette started at 39.91 and will end with a reading of 50.33, that will confirm that we've added exactly 10.42 milliliters. So we've got the burette set up with our volumetric flask underneath it, and you'll notice this is a 100 milliliter volumetric flask. It's got this white line right here showing where exactly 100 milliliters is, and you'll notice I've already got some water down in the bottom. Again, that is for safety purposes. You always add your strong acid, which is the red above. You always add your strong acid to water. So there's approximately 50 milliliters of water in here, but that's not what's important. We're going to open the burette until we've deposited our 10.42 milliliters. Once we've deposited our 10.42 milliliters, then we will use a pipette to add the remaining water until this volumetric flask is full to that little bitty white line on the neck of the volumetric flask. And that will let us know that we added 10.42 milliliters to a total volume of 100 milliliters, which means we will have diluted our acid to our desired concentration.